Okay, so we're back live here with the second presentation of the regional week. So still presented by Roto. So big thanks to our official sponsor, Roto. You can go and see what they have to offer in supplier showcase a little later this week. And we also have JSA as a partner. So thanks to both those companies. With that being said, I'll let you take over this webinar.
Great, thank you very much, Steph. We're happy to have with us today to discuss the subject of solar heat gain with some people who are working with this property from different ends. We have several building advisor firms represented here today, and we also have a representative from Cardinal Glass Industries who are going to be discussing this subject, which is quite relevant, especially in British Columbia today. Maybe I'll begin with you, Einar. If you could introduce yourself, describe your company, your practice, the kind of projects you do, the kind of clients you have.
Sure. Thanks, Al. And I'll preface it by saying thank you for the invitation. We appreciate the opportunity to be here. My name is Einar Halbig. I'm an energy advisor. I've been an energy advisor since the year 2002. I work for a company called E3 Eco Group, and we're essentially a group of consultants and energy advisors. And our primary focus today is helping our developer clients and builders work through the intricacies of the BC Energy Step Code. So we do a lot of energy modeling as energy advisors. We do a lot of blower fan testing. We do a lot of consulting to our builder and developer clients on coming up with a good recipe for them, of mixing and matching different things, including windows and window specs, so they can meet their step code compliance targets. I'm also representative of CASE. CASE is the Canadian Association for Consulting Energy Advisors. And part of what we do is help educate and try to raise the bar of energy advisors across the country by bringing them information like this. So very happy to be here. And that's a little bit about myself and the work that our company does.
Thank you. And over to you, Luke.
Yeah, great. Thanks, Al. Yeah, my name is Luke Dolan, and my company is Capital Home Energy. And similar to Einar and E3, we're an energy advisor company. We're located, we do work throughout the Lower Mainland, Sea to Sky territory, Whistler, Squamish, Pemberton, and we're on Vancouver Island as well too. And yeah, we're energy advisors running around doing blower-door testing on houses, doing building code compliance work, primarily a lot of step code compliance work and air tightness testing and detection of problems that we see in homes and sitting in front of computers and energy modeling. And really happy to be on this webinar today. I love the synergies between energy advisors and I think and the window folks out there. But it's great to be part of the Fenestration Canada crew. We need to come together because there's a lot of synergies we need to learn about windows, and it's great that the window people are learning about what we do too. So really happy to be on the call here today. I'm also a board member, and Einar and I are actually founders of our association, CASE, the Canadian Association of Consulting Energy Advisors.
Oh, that's great. Great to know that. We're talking to the guys who got that going. That's wonderful. So definitely look forward to continued discussions on matters of mutual interest. Mateus.
Hi, again, thank you for having us all here. No, I'm unmuted. Perfect. Sorry. My name is Mateus Alfredo Olmedo. I'm a senior energy advisor working for Luke in Capital Home Energy, and my bulk of the projects that I do are related to the step code and code compliance in the Lower Mainland. So excited to talk about windows and how that impacts the models and basically the analysis that we do and how to fine tune that for our clients, for sort of the clients, for the builders, for the architects, and understanding, sort of distributing the understanding of what a good window looks like and how to optimize that for everyone else. So thank you for having us.
Thank you for being here. And over to you, Jim. Please introduce yourself. Tell us a bit about your company, what it does, and your role at Cardinal.
Okay. Well, again, like everyone else, I appreciate the chance to be here. Cardinal Glass is a glass manufacturer. All of our facilities are in the States, but we distribute into Canada. We make raw glass, we make tempered glass, we make laminated glass, we make low-E coatings and insulating glass units. So all the way up the line, except to windows. We don't make windows. And my job is to understand what you guys are doing with the energy codes and act as an advisor to my window customers then, and to help them sort through the glass options for them.
Great. So we're very happy to have you with us to give us some insight into, well, today it's going to be into the subject of solar heat gain, but certainly topics related to low-E coatings and thermal performance of glass is, I know that's your specialty, Jim, and we're happy that you could be with us today to contribute to our discussion. Mateus, I'll ask you a question here, and I'd like to hear from some of the others too, although the answer to this question might be similar to all of you. How do you see your practice as an energy advisor in British Columbia on these step code buildings? How does that differ or similar to the role that energy advisors might play in something like the Greener Homes program or other incentive programs where energy advisors model an existing house, they model an incremental upgrade and try to report on the savings? Can you sort of characterize the level of effort, the scope of the analysis, and so on? Characterize that for us from your point of view.
So when we look at the foundations of what we're doing is we're using a program Hot 2000 to create an energy model. And in terms of step code or say the Greener Home programs, the only difference is the home an existing home or is it a new construction? So when we look at a new construction, and that's where the step code comes in, we are looking at plans, we are looking at something that hasn't been built yet, and we are advising our clients on how can they achieve code compliance. The step code being a performance metric, there is a little bit of leeway as to how they will build their home. And that's an entirely different conversation. It's like how to make a good step code home. That's where we're coming in. We're coming in at before the permit is issued. We help with achieving permit application. We come back typically at the mid-construction stage to do a blower door test to make sure, hey, are you on track to achieve the air tightness that we're looking for? And we come at the end of the home when the home is built, just before occupancy permit is issued. And we do a final blower door test, do an inspection and analyze the home and make sure that we record all the mechanical systems, we record insulation, the fenestration, and input it into our energy model. And that outputs the step code compliance. Do they achieve the metrics they're looking for? Did they not? When we look at the existing home part of things, it's very similar. It's just that the home already exists. So we start with a pre-renovation energy audit. We come to the home before anything has been done, any sort of upgrades to the home, and we look at the house as it exists. Typically, a mid-construction test could be applicable or not, but there will at least be a final blower door test when all the renovations have been performed. And we do the same thing that we did with a new construction. We look at the home, we basically capture all the envelope components, all the mechanical components, and see, okay, this is where your home is at now. So again, the foundation is basically the same thing. There's an initial sort of energy model. There may or may not be an energy evaluation, like on-site energy evaluation, and then there's a final, which is almost always the same in terms of the energy advisor comes in and records the information. So when you look at it on paper, it's very similar. What changes is what are the clients looking for and how are they achieving the compliance. So existing home, there's a lot more flexibility with how they can, jurisdictions may not necessarily have a specific requirement for what sort of windows they need or what sort of insulation they need. Some do, some don't. Whereas on the new construction, we're building a new home, we have to meet certain energy ratings. So that would be sort of the major difference in terms of, at least for the purpose of for this webinar, is we're looking at there's much more stringent requirements for a new home than there would be for an existing home.
So over to you, Einar. You know, as a let's say you were doing a greener homes kind of a project, would you be making recommendations to the homeowner? Or would the homeowner, or would you just be evaluating something the homeowner wants to do?
So I think there's different levels of answer to that depending on the familiarity and the comfort and the training and experience of the energy advisor. And I think there's to your question that you asked, Mateus, I would sort of address it as there's probably a lot more similarities than differences. At least I think our panel here would agree that ideally an energy advisor would not only be very proficient at energy modeling using the HOT 2000 software, but also knowledgeable about the different options that are available for Windows, so that their model isn't just garbage in, garbage out. The energy model is just software. It's very much based on the user to put in appropriate and realistic, including cost-effective solutions into the model, or options into the model, to help the homeowner, the current homeowner if it's a Green Homes program, or the builder or developer if it's a new house step code application, to come up with an appropriate recipe. So then it sort of begs the question, what's the experience of the energy advisor? And that's what we're all kind of working towards, to help encourage energy advisors to gain more information from webinars like this and training like this, so they can understand more about the implications of what they're going to put in. They can describe anything in terms of performance specs for Windows. We certainly don't want energy advisors to underspec or overspec Windows. Also, energy advisors want to take the whole package, the whole house, into perspective, and they can do that with the benefit of the energy modeling software. So not just the type of windows, but the orientation and the overhang geometry. The more accurately that's represented, the more accurate the energy model can be a tool to show compliance, and also to outline cost-effective strategies that the homeowner or the builder could look at implementing to meet whatever the energy performance targets are, and also the comfort targets, or you can weigh comfort in and factor comfort in, and look at outputs from the energy model that will have very real implications on the thermal comfort of the building. So the energy advisor, with the appropriate training and experience and knowledge, can weigh in with all those different aspects.
It's interesting that you've mentioned comfort, because I've never heard anyone from the energy advisor world talk about comfort in previous conversations. It seems all the focus has been on energy. And in fact, you're raising comfort, and really our solar heat gain discussion today has very much to do with the comfort aspect, as opposed to the energy aspect. Although energy plays a part, you can certainly capture solar heat gain to reduce the need for space heating. But tell us more about your perspective on comfort, and what kind of decisions you as an EA can make, or what would your process be to think about the comfort implications of your choices?
Okay, so that's a great topic. I would suggest that the basic training that any energy advisor goes through, the minimum, it won't touch on comfort at all. It is training that's just designed to educate the energy advisor on the energy modeling software and what buttons to push and how to create an energy model that is accurate, does follow the EnerGuide rating protocols, the blower fan testing, etc. But I think every energy advisor right across the country would agree and recognize that the training leaves a lot of opportunity for more knowledge, more information to be gained, and comfort is one of those things that energy advisors don't get automatically trained on through the energy advisor process. And it's kind of up to the energy advisor to inform themselves about the implications of thermal comfort. And when you do, you start to realize, not surprisingly, that when you start pushing these buttons in the energy modeling software and looking at the outputs, there are absolutely outputs that every energy advisor has access to, particularly in the full house report, of a HOT 2000 model that will give some indication on solar heat gain, how significant that solar heat gain is, cooling loads, etc. So with some, additional knowledge, an energy advisor can read into that and understand the implications or potential implications of this particular specification for windows for this particular house in this particular location. And part of the reason I really like being part of these conversations and salute you folks for bringing this up is, as an energy advisor, as an energy modeler, and same for Part 3 buildings, I know that energy modelers in Part 3 buildings are also very aware of the implications of what you said a minute ago, Al. You can start to make adjustments to your window specs that will allow the building to gain more heat energy, solar heat energy, and that's great for certain performance metrics. But you also want to be mindful of weighing that against the benefits against the added risk of overheating. And the energy model is a great tool to start to do that, as long as the user is aware and has some knowledge of how to do that. So it's one of the things through Casey, for example, we're providing and supporting and trying to help encourage energy advisors to learn more about this and learn how to use their HOT 2000 energy modeling tool to start to infer what the implications on thermal comfort might be like, some of these suggestions they have to meet step code or whatever other performance metrics.
Thank you. That's very helpful. I didn't know that you could get that kind of information, from HOT 2000. Luke, in a conversation I had with Mateus yesterday, I learned that you guys are also using another software tool in reference to a CSA standard in order to determine room by room, or try to get a gauge on room by room comfort levels. Could you maybe tell us a bit about that in your practice?
Sure. I think what you're referring to is room by room heating and cooling loads. So design loads, which is more for mechanical systems. So it's big, and that's directly related to comfort as well too. There's a big problem in the industry with right-sizing mechanical systems, especially with these high-performance houses that we're building now. I mean, we're putting in more insulation, better windows, and more airtight homes. So mechanical systems are still being oversized, unfortunately. They're not, mechanical contractors might not be taking into, and this is a generalization, of course, and I don't want to go after the mechanical industry at all, but some mechanical contractors are oversizing equipment, so they're not picking up on some of the nuances of what we're doing in these high performance houses, right? A home built today at a step 3 level is much different than a house 5 years ago or 10 years ago. And you've got very experienced mechanical contractors that can size a furnace just from looking at the house, but they might be basing their calculations or experience on a house that was built 10 years ago. So they're not picking up on, you might have a USI 1.0 window and you have an effective R30 wall, or you have a 1 air exchange, right? So that's what we're seeing in the industry is a lack of actually having mechanical systems not properly sized for the house. So we do that in-house. So we're doing, and this is actually in the building code. You're supposed to actually have this done in the building code. It's a standard. It's F280 12, and that's the standard in the building code. There's programs like the CHDA's Net Zero Home program, which we're actively involved in, which is essentially the cream of the crop for Canadian home labeling programs. It requires the builder to have one of these F280 12 calculations performed. So that's directly related to comfort, right? So we don't want to see oversizing of mechanical systems. If you have oversizing, if you put a furnace in that's too big for that house per se, you might have problems with short cycling, for instance. So it boils back to the whole comfort thing. So comfort is huge. I mean, at the end of the day, we're looking at, we talk to builders about the emotional side of how to market their houses, and we talk about durability, health, and comfort. And comfort is a big one, right? So we want to be building comfortable homes. We want to be building healthy homes, and obviously we want to be building durable houses. So we are focused on that, and that's something that we push really hard with the energy advisors here at our company, and we're trying to raise that level of awareness through Casey as well too. So broaden that with our membership.
So basically, you're using that F280 standard primarily for right sizing mechanical equipment.
Yes.
And I guess the proxy comfort. So is the comfort aspect more related to making sure that the equipment operates properly, cycles the right way, so that you are actually, conditioning the room to the level you want, as opposed to an inappropriately sized unit that might actually not be providing the level of the temperatures that you want? Is that the focus of the F280?
That's essentially the focus. It's very similar to, so our software that we use in the Energy Advisor world, in the EnerGuide for Homes program, is Hot 2000, and it's got F28012 built into the software, although it's not an approved compliance tool for doing F28012 calculations, and we don't need to go down that rabbit hole because you can spend a little bit of time on it, but we use a different software. And in that software, it's very similar to the way that we model the house. We take inputs like your solar heat gain coefficients of your windows and your USI values of your windows and all the other components of the window to determine what of the house, to determine what the the overall heat loss is, the block load of the home, and also the room by room heating and cooling loads that are going to be required for that house. And essentially, that's to help mechanical contractors size their equipment properly, so that the end result would be greater comfort for that homeowner, so that the furnace isn't coming on, reaching the temperature real quick and then turning off, and then coming back on, reaching the temperature really quick and then turning off. It's hard on the equipment. It's noisy. It's annoying for the homeowners to have that furnace come on and turn off, come on and turn off. The equipment now, it's so sophisticated, but it's designed to run at max capacity. Or they don't want to. You're not getting the efficiencies out of the system if you don't have a size correctly. So does that make sense?
Yeah. No. Thank you very much. Just a note. Have a look at the chat, Luke. There's a comment there that might be helpful with your sound system. Matthias. When we were chatting yesterday, you had indicated that, separate from the use of this standard for mechanical systems, that you also feel that it provides a better accurate read on what the comfort levels in rooms might be. Can you talk some more about that?
Yeah, absolutely. The room by room heat loss calculation, and just to clarify, it's the CSA F326 standard. The F28012 is a ventilation requirement. They're
right. Okay.
Confused. I conflate them all the time as well.
Right.
But yeah, the room by room heat loss gives you a much better understanding of where the heat needs to go. Hot 2000 and software like that, they're really good at capturing the overall heat going into the house, the overall heat going out, but dividing it into different zones is actually where, especially in the high performance homes, that's where you really want to. That's what you really want to. That's really where you want to know where the energy goes in and where the energy goes out. So one of the advantages of having the heat gain, heat loss stuff is that you can find which room is going to overheat the most. You're going to find with the different ventilation, with the different like solar heat gain coefficients for windows, you'll find out, okay, this south-facing room with a giant window, well, this is the one that's going to need the most cooling. You don't need to necessarily need to cool the entire house. You can actually have a much more informed approach to how you're creating the home. So overall, like, for instance, step code is great at dividing the performance of the home in terms of mechanical systems, in terms of envelope performance, in terms of air tightness, but it doesn't give you the specifics of like, okay, which part of the room really needs that cooling, which part of the room needs which part of the house is going to need the more heating. So when you look at the more granular room by room heat loss analysis, you really get a good get a good sense of like, okay, now I understand that this is the living room most likely is the one that's going to need the most cooling. So you can make a much better informed decision with that.
So potentially you could choose a different solar heat gain in the living room to moderate that as well. Is that right? Or would
that is a design granularity of design that is really useful to have, and you can have an optimal house designed in such a way that you actually have different rooms that have entirely different windows specified for them, which would allow for most likely to get the most bang out of your buck. So having an energy advisor consult with you to sort of find out what you need is probably the best option, and start having a conversation early on before you even design the house, before you have a final design. You can actually come up with something. You can actually come up with a good solution for that. You can start analyzing different ways and like different ways to optimize this. And there's the integrated design process, and both Einar and Luke can speak more to it. But basically, getting all the consultants, all the architects, all the engineers, all the energy advisors together before permit is issued, you can get together and go, okay, what do we need to do to achieve this high performance elements, and what needs to change for them?
Well, I think this is a good segue to Jim. I know that Jim and I have had some conversations about the fact that sometimes you do want to choose different kinds of glass for different orientations to handle something like solar heat gain, which can be problematic if you have too much of it. Not that that's the focus of the next question, Jim, but I just thought I'd connect Mateus's comment. That energy advisors who know how to use this CSA F326 standard and tools do have access to a tool that'll help them to, I guess, quantify potential overheating effects in a building. But not all energy advisors are using that software. That's kind of, I think this is a higher level of service that I think you guys are providing under the STEP code than you would expect just any energy advisor to be able to provide. And perhaps energy advisors without this kind of deeper training might benefit from rules of thumb kind of guidance. But Jim, I know that we've asked you to share some thoughts on solar heat gain, and especially, sometimes we think solar heat gain is this uniformly available resource everywhere you are, and you've done some research to look at how it might vary with location and orientation. Mm-hmm. So I'd like to turn it over to you to share with us what you've prepared.
Okay, I want to offer up one comment on the comfort discussions that we're having. Is that sure. Historically, and at least in my experience here, is that the energy analyses programs don't handle shortwave radiation very well. So think about that as the comfort offsets that you get in your car driving, with the sun shining directly on you. The temperature in the space may be okay, but you're uncomfortable because of that shortwave gain that's directly on your body. Few of the programs actually analyze that. In fact, when they go through and do an MRT, a mean radiant temperature, mostly that's in the center of the space.
True.
It's away from the window. And so critical to that window discomfort question becomes, where are you relative to the window? And are you picking up the offset from shortwave as well as room temperature effects?
Sounds like words of wisdom here. Because you're right. The ASHRAE 55 type analysis is a center of the room analysis, and may not work as well at the edges.
So, and it's long wave.
It's long wave, right? Yeah. Okay. Yeah.
So, well, okay. I've put together a bunch of slides here. I'm not actually going to talk about glass at all. I'm going to talk about environmental conditions and temperatures and solar radiations, and go back to the point you were making, Al, is that it's not the same everywhere, and it changes depending upon where your building's at, what orientation you're on, and you have to be cognizant of that. The good news is on the glass side is that we've got multitudes of products available to to engineer into every particular situation you've got. There's high solar gain, medium solar gain, low solar gain, low ease, multiple layers. We talked about a 0.8 U factor. Those types of products are available. The only caution I would give you is that I can't produce the solar gain of a single pane clear glass in a 0.8 window. That's in the laws of physics, that's called unobtainium.
Right. In other words, and here's the thing, under the BC step code, I would assume that most buildings are now going with triple glazing to get to step 4, let's say step 5, right? And in that case, Jim, you're talking triple glazing and probably 2 low E coatings for thermal. What are the realistic center of glass or whole window solar gain ranges would be?
You're going to be, below 0.5 is the maximum that you can achieve in a window frame. So just to think about this triple pane with 2 low E's in it, it's the equivalent of 8 panes of glass in terms of its insulating value. And so basically what a low E coating does is it displaces a layer, but we don't magically gain back all that transmission that we lost with that layer. So you follow this curve of U versus solar heat gain. That's a function of the layers or the equivalent U factor then.
So basically you can choose your solar heat gains. You're just choosing from a much narrower range.
Yes.
That's available, when you've got 3 panes of glass.
As you tighten up on that U factor, as you drop it down, you're going to crop the solar heat gain then as well.
So realistically, are you somewhere between 0.2 and 0.4 as a range?
0.2, 0.5, and as the upper end, depending upon a skinny frame or something like that. Yeah.
Okay. Yeah. Anyway, it's kind of a good to know as a rule of thumb, right? So. Yep. Yeah, but please carry on.
Okay. All right, so I'm going to share my screen here, and I've got a couple of quick slides I'm going through. It's just going to be looking at some weather conditions and giving you a little insights on solar exposures. As soon as I get them. Is that screen coming through? No, I have to hit share. There we go.
Great, that's it.
Now we're seeing it here?
Yep.
Okay, so quick example here. I'm gonna be doing a comparison between Vancouver and Winnipeg. Kind of give you 2 extremes of weather conditions. And this plot is an annual minimum maximum by month of the temperatures. And this is read directly out of a weather file. You can see it's Vancouver's not very exciting from the temperature aspect. Winnipeg is. There's a lot more variety there, but go back and forth here, and then this is really what's going to be affecting your maximum building design loads. Now we look at a distribution of the temperatures themselves within the year time period, and I've binned these together in 5 degree C elements here. So look right here at near freezing in Vancouver, you got about 1,000 hours. In Winnipeg, you still got that 1,000 hours, but you got all this stuff down below here. So this is really changing the profile of what the heating loads are like there. If I take this now and convert it to a degree day, the blue bar is representing heating degree days, the orange bar is representing cooling. You can see the profile of it, peaking at the end of the year, the beginning of the year, and then peaking in the summertime here on the solar side, or on the air conditioning cooling side. Now go to Winnipeg. Obviously, you've got big peaks on the ends of the plot here, and you actually have a higher amount of cooling demand in a Winnipeg than you do in Vancouver, all a function of that temperature and the solar exposures. Here I did an overlay on these plots. It's the same information you've seen, but you just see the profile of the maximum temperatures here for the month. There's the profile of the cooling degree days that follow that. Here's the profile of the minimum temperatures, and you see that the endpoints here is the heating degree days are maximized. Now here's Winnipeg. So we're just more demonstration of the extremes that you've got. Let's take a look now at the solar conditions and what we've got. So go to Vancouver, daily average solar radiation. On the north face is that this is not your passive orientation. If somebody's got a north facing building and they want to build a passive house, better tell them to pick it up and turn it at 180 degrees, because it just ain't going to work with that kind of a solar exposure. Here's the east and west orientation in Vancouver. Again, the radiation's peaking in the summertime, and there isn't much available on the heating seasons here to offset those heating loads. But here's your south face of the building. Not as much as you maybe could use, but some peaks here into the spring and fall. And here's all four of them mapped together. Next slide I'm going to have is going to be Winnipeg. It's actually fairly similar in the shape, but there's a big difference in the tails here in terms of the winter season exposure. Notice how much sunlight you've got here in a Winnipeg at the end of the seasons, during the heating here, than you do in Vancouver. Now I'm going to do an overlay again on the heating and cooling degree days. This is the south face there, and this is the west face. So this would be driving the air conditioning on the building, and this is the chance to offset heating loads. Well, what you see here is the peak in solar gain on the south face of the building is during the time of the season when the heating load is actually starting to go down. Same thing here is that the solar gain is going way down at the end of the year as your heating load is going up. So to get to total passive effect here in a Vancouver climate is going to be a tough design criteria. Whereas you go to Winnipeg and you see that solar holds up much longer towards the end of the seasons here, and it's obviously then driving the air conditioning here in the summer. So where does that come from? Well, here's a January solar. This is all 31 days in January, and you're looking at the solar gain every day there in Vancouver is at, what do you got, 7 and 9 days a month where you've got sun shining, and it's pretty cloudy the rest of the time. So the passive solar availability in Vancouver isn't great. It is in Winnipeg. Winnipeg, you got only 4 or 5 days a month where you don't have the solar gain there. Come back to the summertime here, and Vancouver has got pretty uniform sun and shiny here throughout the entire month, as is Winnipeg. So I'm coming to the conclusion here is that when you're doing passive solar design in a Vancouver in particular, you've got to be cognizant of that solar exposure, because you're not going to satisfy the building every day of the month. You obviously have going to have backup issues here. If you end up designing to to this type of solar load, and then you come back up to this day, this is going to be massive overheat. You got to use some caution here and to how you achieve this balance then. So the last thing I've got is that I can do this for any other climate here. So here's Summerland, here's Toronto, 2 other examples just to show how you can do those plots. The last thing I looked into here was the question of an overhang. I don't have final answers on this, but I've got some trends that I can at least show here. Complex slide, but let me show this up here. Is that this gray line right here? This is the beam radiation on the south face of the building in the summertime. This dark orange line is the gain through the solar exposure on the window with a 0.1 projection factor.
Could you define 0.1, Jim? In
Uh,
other words,
0.1, that's the ratio of the projection to the height of the window.
Okay,
So-
so let's say a 10-foot high window with a 1-foot
Yes.
overhang.
Yes.
Okay,
And so that's kind of the universal nomenclature that's given to the overhang discussion here, is that what's that ratio of how much depth the overhang has, or how much it projects out over the face of the window.
so
That then is
that the projection factor then?
that's called the projection factor.
Okay,
And that's going to define then the shadow lines on the glass. So think about the angles that you get. If I had a 0.4 projection factor is 4 times deeper. And so you're obviously going to block out a lot more of that sun. And that is exactly what we do right here, is that on this summer day, that 0.4 projection factor blocks a lot more of the sun than you do with the 0.1 projection factor. So that overhang is giving you that control and getting you away from this full exposure up here. Now we move to a winter day, and sorry guys, I got way too much information on here, but again, I'll point to there's the solar exposure for that winter day. There's the 0.1 projection factor, and there's the 0.4 projection factor, all because of the solar angles and the sun for the summer versus the winter. In the winter, the sun is low in the southern sky. It's down below the shelf, or the overhang, if you want to call it, and it's allowing most of the window to get exposed. Whereas if I go back here, is that the sun's higher in the sky, and that projection then is giving you a lot better blockage on that. So a very effective tool. And this is not talking to the window solar heat gain. This is talking to the exposure that the window has had.
so this chart is the summer chart?
This one is the summer. This is the cooling today. Yeah.
Right, July, okay, yes.
And
So,
then
yes, so
this-
because
yeah.
the sun's higher in the sky, less solar heat gain. Now the sun is lower in the sky, this is winter.
Yep.
And we've got much higher solar heat gain, and the projection factor isn't doing much.
And the relative, heights of these are what you'll modulate with the solar heat gain of the window. So here's a great tool where this is the sort of the first, what do I want to call it, dynamic window, is that it allows the sun to come in when you have an overhang in the winter time, and it blocks it in the summertime. So this is a building design attribute then to be able to get some control on that exposure. Kind of where I'm at. Yeah.
So this is really why, let's say in the passive house world, you want to capture the solar heat gain in a south-facing orientation.
Yes.
You don't want the east or the west because you can't really control that, right?
Right. And I want to go back to this one right here, is that you want that south exposure because the sun is there in the wintertime, but be careful of the sun that you put on the east, what solar heat gain you put on the east and the west. I mean, if you do from the design aspect of the building, you're better off having low solar gain windows on the east and the west, minimize the risk of overheat, minimize the cooling load altogether, and then provide the passive effect on that south side.
Where you also then need to consider possibly the need for some overhang at least. You may or may
Well,
not.
I didn't even show this up there. No, Al, I don't think there's there's much of a benefit to overhang on the east and the west.
No, I meant the
because
south.
On the south,
Yeah.
obviously, yeah.
You're right. On the east and west, it doesn't matter because you're going to
The
get,
sun's gonna go under it, yeah.
yeah, it'll go under it.
Yeah.
Yeah.
So I think part of the message there is that the glass industry, the window industry has a full library of glass products available. High solar gain, medium solar gain, low solar gain. All of them have virtually the same light transmission characteristics. So you can put one solar heat gain on one elevation, put a different solar heat gain on another elevation, and design and optimize your building on a per elevation basis then.
But what your charts are showing us though is that the idea that, well, if I just have higher solar gain windows on all the window package for the home, I may not be actually reducing. I may be showing that Hot 2000 may show a net reduction in heating demand, but I am going to be pumping a lot of heat in at the wrong time of year.
Right.
My east and west windows are going to be pumping in tons of heat when I don't need it. And
a high solar gain window on the east and the west orientation will have some wintertime benefit, but you'll pay for it in the summertime.
Yeah,
even if you're not
for it the rest of the year. Yeah.
Even if you're not air conditioning, you'll pay for it from the context of comfort. So you have to be cognizant of what direction you're facing those windows at.
So this is one of the things that we've heard. One thing that's frustrated the window industry, I'll just make this comment here before you continue, Jim, is that they've had some energy advisors asking for higher solar gain for the entire window package, and they're thinking that solar heat gain is like it's like
a universal.
It's a free universal heating source, and the more the merrier. Wherever you put it, you're going to benefit. But not appreciating that you may be drawing in a lot of excess solar heat gain when you don't want it. And if you don't appreciate that if your big windows are facing east or west, you're probably not going to have a very happy occupant in that home.
Careful about where your view is. Yeah.
Yeah. Right. So, where do you want your view, and is that a room you want to bake in or not? So, I think this is something that, the whole idea of passive solar heat gain, we should not ignore the experience of the passive house people, where they say, focus it where you can use it. And that's a south-facing winter orientation, and control it, if you need to, I guess, add solar shading or an overhang for the summertime of that solar facing window, if the building geometry itself is not sufficient to provide that shading.
And now you're going from a passive homeowner to an active homeowner if you have to add shades on the inside of the window.
Right. Yeah.
Then so they have to be cognizant of that they're part of the solution then, if that's the way you work it. And regardless of if they're going to get involved in it to that extent, you kind of lose the window then. If you can't see through the attachment, what good is the window at that point?
Right.
I would agree with that 100%. I think that's a very much overlooked implication, that all of a sudden your homeowners, like, and Jim, your terminology is great, are going from passive homeowners to active homeowners, because they have to end up getting involved to regulate the amount of solar heat energy that's coming in.
And they can do it. They can do it, and they can do it well, but they can also do it really bad. And I would tell you is that just driving around my neighborhood, particularly in the wintertime, and by the way, I live in Minneapolis, so I'm a lot closer to that Winnipeg profile that we've been showing here. And what I notice is that in the short daylight hours of the winter, people tend to close the drapes and blinds down, and they don't actively open them up during the day. So the promise of this passive gain isn't realized. It isn't like everybody goes to work in the morning and gets halfway to work and says, "Oh, I forgot to open the blinds," and they turn around and go back. That it's just it doesn't happen. You got to have a homeowner that's cognizant of the influences they have.
So
okay,
please carry on, Jim. Yeah.
Well, this is my last slide, Al, and this was the question. Actually, we led into this a little bit. Is that in the analysis software programs, whether it's Hot 2000 or I'm using Energy Plus predominantly to generate some of these curves, is that you've got to be careful on is it doing MRT on long wave energy, or is it doing the short wave offsets here? In most of the situations, I've had to develop an offline spreadsheet to take the hour by hour solar radiation and create a PPD, an offset directly to the predicted MRT on every
By
hour.
MRT, you mean mean radiant temperature?
Mean radiant temperature. In PMV is the predicted mean vote. This is a comfort term, but there are correlations that you can use to do the sunlit offset. But I don't know Hot 2000 well enough. Does it calculate that? Does anyone know?
Does anyone know?
I don't think it gets that advanced. It definitely does account for the amount of solar heat energy that comes in based on the weather profile and temperature profile and a solar availability profile for the particular location that the energy advisor chooses, as well as the specifics of the window makeup, the geometry of the window, the orientation of the window, and the overhang geometry.
Mm-hmm.
So it does factor in a number of things. I don't know enough about it to judge whether there's anything important that would be missing, but those are the things it does factor in.
It's been my experience is that when the room gets up to temperature, when there's enough solar gain into the space that it shuts off the thermostat, in essence, shuts off the heating plant, then you're riding along free. But it doesn't know if you're 2 degrees above thermostat or 10 degrees above thermostat. It's not making an analysis on that, and that's something you've got to be cognizant of, as a question of how much window area you've got and all those details.
Yeah. So I'll just add to that quickly. Hot 2000, it doesn't give you any warning about temperatures are climbing. The energy advisor has to know where to look in the results to ascertain that based on the available information out of the energy model. And it also doesn't look at the situations on a room by room basis. It looks at the whole building numbers. So it won't give you a warning, and it won't tell you, even if you're looking for information, you won't necessarily get it about how much does this particular room potentially overheat, or how much free heat energy does that particular room get.
And then the really critical thing on the windows isn't the building average, it's the window to floor area ratio for each room. And, that's what you really need to look at to understand what the discomfort potentials are.
The use of CSA F280 that Luke talked about earlier, the room by room heat load and cooling load calculations, that I think is a very good tool that's sort of accessible for energy advisors to learn about, that can provide more information on how the individual rooms respond depending on geometry and the window implications.
But it may not take into account the shortwave radiation effect that Jim's talking about, that you might be exposed to the direct sunlight from the window. Let's say in a room with a large window to floor ratio, right? that the like you said, the temperature might be right, but you might still be exposed to overheating, especially if you're in the beam of the sunlight. Jim, did you have one more slide there? Or
No, that was it, Al.
Okay, great. Well, thanks for sharing that, Jim. It's certainly added to my knowledge. In fact, everything you guys have said has added greatly to my knowledge of the kind of the the tools and the environment you're working from, the products that our industry sells, and how the two come together, to provide a home that's comfortable as well as energy efficient. And I must say that it's been very interesting to hear the comments. Any closing thoughts from anyone about today's session, or anything that you think we should explore in a future session on this topic?
Al, it's Terry. I'd like to jump in just really quick. A couple of things that I heard that piqued my interest. Jim stated they have a multitude of coatings, and they certainly do, as do some of the other window suppliers. Most window manufacturers have hundreds, dare I say, thousands of models for their product lines in a wide variety of variations, U values, and solar heat gains. But my experience was almost exclusively we would get a request for this U value and this solar heat gain. There was discussion about different glazing options on different elevations, different solar heat gains used on different elevations. And I think that this industry is headed for a transformation in that, we have products that can handle solar gain. Mm-hmm. We have very, very low U value glazing options in products. And I think that as these homes get more efficient and the technology pushes further with mechanical systems and that we do need to be mixing glazing options and glazing designs to grab these values that are appropriate for the design and the elevation orientations. And I think that this is a great conversation to start directing EAs and manufacturers to start looking at and promoting the performance attributes of certain packages and certain window designs that can be used effectively to minimize the negative aspects of things like solar gain. So great conversation. It was really interesting.
But potentially that puts more work on the energy advisor, who, instead of using the same glass package through the whole house, now might have to have more options to add to the analysis.
Absolutely. And so they should. Sorry, guys.
That might be a very a good, financially beneficial trade-off for the client, the builder, say, to allow his or her energy advisor to spend a couple more hours sorting that out, to save. Maybe it avoids the need to go to a more expensive type of window. Upgrade from double pane to triple pane or something like that. So the modeling, certainly energy advisors would promote the modeling is a tool that can and should be leveraged to investigate some of these opportunities and see if there's a realistic opportunity to save a lot more money than the modeling cost when you're actually building the house.
Control the heat gain on the east and the west in the summertime, and you minimize the size of the cooling plant. And so there you go. There's some dollar savings right there. So you got to figure out how to not get the east-west windows installed on the north and south side.
Well, they probably won't fit.
That was going to be my answer, is that make them different size.
These days, it's hard to find two windows of the same size in any house package. So
that's for sure.
Any comments from you, Luke?
Well, I love this discussion because solar heat gain coefficients, especially in window orientation and the amount of windows, and Jim brought it up to the window to wall ratio, all very important. And what we're seeing with these, especially high performance homes, are the internal gains become much more important, right? And those are the gains that the human occupants give off, the heat, right? Your hot water tank, your refrigerator, your freezer, your computers, all of this is giving off heat. You add the wrong coatings on the window, all of a sudden, you've got the house overheating. And in our climate zone, which is a tough one to build in, because I love your slides there, Jim. It'd be interesting to see them updated after this summer that we just had, where we were having 40-degree temperatures during the summer. But in January, you're right. I mean, last year we set a record rain 29 days of 31 or something. But in February in Vancouver, it could be 15 degrees Celsius, and the next day it could be -5. So it's a really tough climate to build in, and let alone install windows in. And you don't want air conditioners turning on in the middle of wintertime. So the internal gains become such a big thing. I mean, we've learned, and the feedback we get from clients in the real world, where we've had homes that are overheating, we always go on the lower side with the solar heating numbers. And it's like you said, for the south and west facing windows, if you want to go higher gains for the north and the east, for sure. But we don't see that enough, and I think it should be done more.
And would it be a stretch to say that if you want a rule of thumb for a highly energy efficient home, like a step 4 or 5 building or a net zero home, you really don't want high solar heat gain anywhere unless it's maybe a south facing window that you're consciously trying to harvest heat from? And if you don't really have a passive design strategy, why would you want anything more than a moderate solar heat gain anywhere in that house? Because you're not likely to capture much in the north, especially here in Vancouver. And you pretty much don't want it anywhere else, especially if it's highly insulated to the point that internal heat gains can lead to overheating. Would that be a stretch?
No, I think that's you must have your hammer there, because you're hitting nails on the head there, Al. I think that is very much a key message, that we're coming to the same conclusion from different angles, and I think it behooves all of us, window suppliers, window sales reps, builders, HVAC contractors, like Luke talked about with the sizing, and energy advisors, to understand where things are going. And I just kind of reiterate what you said, Al, because I think it's super important. Step code is moving us towards better insulated buildings, and they will retain more internal heat gain energy, like Luke talked about. And all of a sudden, it's a paradigm shift. We've been in the industry for 20, 30, 40 years, and we've been learning about, passive solar heat gain. You want that. That's free heat, after you spend all that money on those triple pane windows. But it's free heat, right? And all this great stuff. And look at the angle of the sun and all those wonderful things. But then people start living in houses that have some of those elements incorporated, and all of a sudden, I have issues with comfort and control of this heat energy. And somebody mentioned the passive house buildings. There's some in Vancouver that the industry has been learning from, and they've been fortunately sort of okay to talk about that. And let the industry learn from the idea of a super insulated, very airtight building, all of a sudden, and not surprisingly, becoming very susceptible to overheating when a little bit of sunlight trickles in through those south facing or maybe those west facing windows. And now, because it's so well insulated and so super airtight, how do you get rid of that heat energy? Now it's a big problem. So I think the whole industry needs to be aware of this and change the mind frame a bit from passive solar heating being, good, and the more the better, like somebody said earlier in the talk, to it has serious implications, and we have to be, I think, much more cautious about its use. Otherwise, we are going to literally be dooming these buildings to being uncomfortable. And the writing's already on the wall. Right, it's already happening, and it's in the energy model, whether it's Part 3 or Part 9 buildings, as long as you know to look for it and are aware of it. And it's in the F280 room by room heat load calculations, cooling load calculations, as long as you know what to look for. The more you get educated on it, the more you'll realize that it's important to be very cautious about the solar heat gain coefficients and the amount of solar heat energy coming in as we move towards more energy efficient buildings.
Yeah, Lot 2000 really benefits from a high solar heat gain. So you might be thinking, is your energy model like, oh great, I've got a high solar heat gain here, so we're getting that free energy. But we know in reality it's a double-edged sword. We know that, hey, and an experienced energy advisor should know this, and it's really, really important to be talking about solar heat gain coefficients, because it can make or break the house meeting the step code target. So if an energy advisor wants to do a really high solar heat gain to meet a target, well, sure, but then what Einar just said is you're gonna have problems with that house. It's not going to be comfortable. The homeowners are going to be not happy with the end product. So it's a really important piece of the puzzle. Sorry, Terry.
Yeah, it's okay. Here in BC, there's lots of us that are talking about this challenge, but something that surprised me was some of the information that Jim shared about a home in Winnipeg. You would think, okay, Winnipeg, you want to grab as much solar gain as you can, but in fact, if you're not managing, overhangs and some sort of strategy for shading in the summertime, that Winnipeg home is getting a lot of solar gain. And I expect that they're having problems in buildings that are not well designed to manage that solar gain in the summertime, in the prairies, places like Winnipeg. I was surprised to see the numbers of solar gain in Winnipeg in the summertime.
And I would back that up from the standpoint that in my experience of tracing code histories and looking at what's going on to the building as it's better insulated and we're air sealing it and things like that, is that the utilization of solar gains is reduced in these more efficient buildings. You can't accommodate everything that comes in. So, it's a different, you know where you're at with the step 4 stuff. You can't bring all that sun in and actually utilize it.
Well, I think that's sounds like a good place to end our conversation. We're at time here. But I really want to thank everyone who participated in this discussion. It's been very informative to hear from you, and really appreciate your contribution, Jim, with some data to kind of help us appreciate location-specific variables, but also some general principles that would apply in all cases. So thank you very much for kind of quantifying that for us and displaying it in the graphs. It's been such a pleasure talking to you guys. I think there's probably more we can do to provide some practical guidance in the future on this subject, and we certainly look forward to speaking with you again, or even collaborating maybe through some group with Casey, maybe FenCan or something like that. I think it would be really helpful if we could provide your industry with some clear guidance, even if it's in the form of rules of thumb, that could help to drive right decisions early on, so we don't have people going down rabbit holes and creating problems that need to be managed, but just providing more thoughtful guidance right at the beginning as to what is the right, call it a kind of a pattern language or something, for step 4 homes. They're just going to have certain characteristics that are not typical of the homes we built 20, 30 years ago. And so maybe there's a way to more formally encapsulate this knowledge and pass it on in a way that'll be helpful to the practitioners. That would be great. So we would look forward to working with you on something like that. But again, thank you to Luke, Mateus, Einar, Jim, Terry. It's been great talking with you, and we hope that recordings of this session will help people who were not able to be present today. But this stuff's going to be available and persist on the web and be maybe part of a library of useful sessions to help people engage with the subject matter. And just one final correction. We've been mentioning F280 a lot, but we were corrected a little while ago that the standard was apparently CSA F326.
It's the other way around. I stand corrected.
It was the other way around? It is
F28012. I confused it as I said.
Okay, okay. All right. So
280-12.
Conclusion, it is F280-12 CSA standard, which is the standard then for doing this room by room analysis, which is kind of center of the room analysis, I guess. Well, it's more for heating and cooling loads, not necessarily comfort. So it gives you some guidance, but it may not be on its own maybe the perfect tool in all cases, especially if you had large windows. So, but thank you very much. And look forward to continuing the discussions.
Great.
Great.
Thanks for having us.
Thanks, everyone.
Take care.
To everyone.